Okay, so everything we are still looking at is second order differential equations, but now what we're adding to this is we are going to add non-homogeneous. So if we recall last time, the homogeneous functions, right? Everything we did in section 3, it's equal to 0. The only thing we're about to change is we are going to now make it equal to a function. All right. The one that is equal to 0, right, is called the associated homogeneous function to the non-homogeneous function. The good news is that because, all right, we've already done a bunch of work solving the homogeneous equations, there's basically the only difference is if I bring this function to the other side with the solution, right? Because we've basically been saying yt equals a function, and we have our 3 versions, right, of solving the parabolas, right, of what y1 and y2 are. Then all we have to do is figure out what the other piece is. Now, because it's not important to the actual solution, the proof is here. Again, if I was Dana, I would go through it slower, but there it is. The point is what that theorem does for us. Because a homogeneous differential equation and a non-homogeneous differential equation line up so well that actually the overall solution, all right, the general solution that we're going to find breaks into 2 pieces. All right, a complementary solution and a particular solution. The good news, the complementary solution, that's what we did in everything in chapter 3. So we're already going to know how to solve this piece. We solve the characteristic equation and we get that guy, all right, or even, some combo using reduction of order. Then, all right, we have to identify the particular solution. All right, and basically that's what the next several sections are about, because this can be a little complicated, but we're going to actually see a couple of methods that break this down really, really nicely. Those 2 methods are undetermined coefficients and variation of parameters. So undetermined coefficients is without a doubt the most common approach, because it basically identifies, all right, we identify what g of t is, all right, in this equation, and we basically say, well, there's usually only a couple types of functions that everything breaks down to. The most common functions that occur, all right? Now, the disadvantage is that it says, oh yeah, it only works on a small number of classes, but these happen to be the most common functions that there are, all right? And the method is simple. We basically pick some constants in our equations, and then we will solve for what those constants are. So based on particular g of t's, okay, and these 3 are all the same. So really there's just 3 cases, all right? Exponential function, sine and cosine, and a polynomial. Is that most functions? I mean, that's a lot of them. Like, that's got to be a high percentage. So we'll create a general equation, and then we'll solve for these constants. And this actually ends up being, solving for the constants is not fun, but creating the functions ends up being a lot of fun. So let's look at some examples. So, all right, we have, all right, a second order differential equation, but now it is non-homogeneous. This is now not equal to 0. But we're going to start with the same approach that we did. Solve. I need to have the equation. All right, so we're going to solve the associated homogeneous differential equation. And in order to do that, right, we create the characteristic equation. And this is lovely factorable. What are the factors?
-6 and +2.
Yep. -6, +2. Just make sure we're on top of that. Which gives us R equals, now, instead of this being, because we would get right to our general solution, this is now the complementary solution. This is why everything that we did in chapter 3, the home fund that you're working on, it should be a piece of cake, because I was like, it's really just half this problem. All right, so basically, this is the same problem, it's just twice as long. Doesn't matter which one is first. But. So we create our complementary solution. Okay, now here's where the meat comes in. In order to do the particular solution, we identify our g of t function, which is 3e to the 5t. And basically we make a guess, all right, for what the particular solution is. Now, as we start off, the guesses should be pretty straightforward, because I'm pretty sure this is going to line up with exactly what we have. Oh, look, all right, I have something constant to an exponent. Oh, well, that means the guess is exactly a constant with that same power in the exponent. Because our whole goal in finding a particular function is going to be to identify this constant A. So, all right, as long as that matches up, and again, this is the most basic case, all right, then, all right, the issue, this is why it's called undetermined coefficients. This is the coefficient, okay, and now I have to determine it. In order to determine it, well, gee, I have a function, and I have a second order differential equation. What do you think we need to do?
Oh, derivatives.
Yeah, just like we do with our IVPs, all right? We need to take a couple of derivatives, and then we're going to substitute that in. And then so I'm also going to simplify this down. Now also notice that I'm plugging this in to the not the entire, not the associated, because the point is I need to figure out what A is. And then, simple solve. All right, the e to the 5t's can basically go away, so I have negative 7a equals 3, right? So a equals negative 3/7. Which gives us our particular function. And hence, all right, the whole point here is that y of t is equal to the complementary function plus the particular function. So it is just a summation of these two pieces. And this, all right, so this is again, this is the general solution. So notice that our general solution is very similar to what we had, okay, but it's got a little bit more on it because of that particular solution. Finding that additional coefficient for the undetermined coefficients guess, all right, that's where actually most of the work lies. However, this actually was an IVP. So one last step here. We need to apply our initial conditions. Because of that, right? So these are still initial conditions of 0. Because of that additional g of t function, right? We end up with this. So don't forget, before we go plug in this into our matrix, this needs to be brought up, right? So that does just become a constant since we're solving for C1 and C2. So make sure you bring that over, and then you can plug that into the matrix. Which gives us our final solution, the actual solution, all right, with our constants. Now, here's a big note. As we get more into, this is essentially the first and last IVP we're going to do. We're going to, even though those last steps aren't difficult, we're going to spend most of our time trying to identify the G of T proper, the particular solution, all right, versus doing the plug and chug IVPs. You're doing tons of that in chapter 3. I was like, basically, you're going to get the gist. IVPs never really change. There's not much to them. So we're going to be identifying most of the time general solutions. So we're going to stop, all right, with C1 and C2 most of the time because our work is identifying what the particular solution is, just so you're aware. But was it hard the last step? No. IVPs just add one more step that we get it now. We've done enough. All right. I want to find the general solution for the following differential equation. Oh, good news. I was like, what about the associated homogeneous function here? Does that one look familiar? It's literally the one we just did. All right. So notice that the complementary, and we're going to do several of these because the point is going to be the other side. All right, so that leaves the particular function. G of t equals sine of 2t. So it all comes down to guessing the particular. And even though I have three methods here, it's just to emphasize that no matter if it's just a sine or just a cosine, every time the guess has to include both. All right. And we're definitely going to see that when we do solving, that if you just guessed half of it, your answer is going to be all messed up. By definition, the whole point of the undetermined coefficients method is you have to make the proper guess for the particular. All right, and we're going to see that this will get more complicated and just have to focus, all right, on what the coefficients are. So that means the guess should be a cosine, all right, and the angle is always what's specified. So we're not guessing that part, right? We're guessing the coefficients. We know this is cosine 2t. Once again, then we can just do some derivatives, all right? And solving this is where we're going to focus. Because notice that in this one, was I solving an IVP? No, general solution. So that's basically, like I said the last time, because all the work is going to be in finding, all right, what a particular solution is. So you're going to have two constants in this equation already. We don't want a lot more time. All right, then plug all those y's into the equation. And this is where the work starts to come. Okay. Once I'm here, all right, then the other thing, all right, so I get this down to some signs and sign A, sign B. I was like, that's about as much. There is a nice thing I can do, all right, and this is an algebra principle. So I want to group the signs together, all right, with the coefficients. Because remember what we're trying to solve. The temptation a lot of times is, oh, we're trying to find the t right inside, but that's not what we're doing here. I have a function sine and cosine, just like you have, right? You isolate them to solve for the coefficients in front. So I'm going to rewrite this, all right, as the co. And that right there is a pretty big deal.
Is it frozen?